Hello class, this second part to this lecture series here will cover the 6F50, 6T70 electrical operation, hydraulics, and some improvements that they've done to this transmission. Starting off with the Ford 6F50 and looking at their solenoid body. You're going to see their solenoid body only contains the solenoids. It doesn't have the control module like the GM unit does. And they do have an on-off. Their shift solenoid E is an on-off type. What it's going to do is control a multiplex valve. And you're going to see what that multiplex valve does. You're going to see it allows the solenoid D, shift solenoid D, to operate either the low reverse clutch or the 4-5-6 clutch, depending on the state of the multiplex valve, which is controlled by shift solenoid E. So by utilizing shift solenoid E, they're able to allow the use of their pulse width modulated solenoid D to control either the low reverse when you're in low gears or the 4-5-6 when you're in higher gears. So as I just mentioned, shift solenoid D is going to be controlling the low reverse and the 4-5-6 clutch. It is PWM, linear, however you want to call it, electronic pressure control solenoid, and it is a normally passing linear. So that means when it's electrically off, it's allowing hydraulic fluid to pass through it and reach the clutch component. We also have shift solenoid A, which that's a normally trapping PWM solenoid. So it's also PWM, but it's normally trapping. Another terms for these are going to be inversely proportional or inversely proportional. You'll hear those terms passed around. Proportional means that when it's off electrically, it's off hydraulically, and when it's on electrically, it's on hydraulically. Inversely proportional, as you can imagine, when it's off electrically, it's on hydraulically, and when it's on electrically, it's off hydraulically. So the normally trapping, so when it's off, it's preventing fluid from getting to the clutch component, that would be the proportional. And then where you have a normally passing linear solenoid, that would be inversely proportional. Okay, so also on the slide we talk about the torque converter clutch solenoid, and it's a normally trapping solenoid, so meaning when it's off, fluid does not get to the lockup valves because it's going to be used to control torque converter clutch pressure. So what we then have is a proportional solenoid for it. Shorten that down to prop, so I don't have to spend so much time spelling proportional. Another term that you might hear is normally high or normally low. So normally passing would be the same thing as saying normally high. So normally high, NH, is the same thing as inversely proportional, which is the same thing as normally passing. And normally low is the same thing as proportional, which is the same thing as trapping. Other solenoids that we have shift solenoid B, C, and then EPC, which EPC is basically just line pressure control. But the shift solenoid B is going to control the 3-5R clutch. Shift solenoid C is going to control the 2-6 clutch. So we have individual solenoids controlling individual clutches. And you're going to probably guess that the design of this electronic system is that they're going to put a lot of emphasis on the computer controlling these solenoids, which are going to control some valves to control pressure. And so our shift quality is going to be hugely dependent on the operation of these solenoids and valves and the pressure going to these clutches. Here are the layout of those solenoids and how they're hydraulically fed with pressure. They're fed with pressure from a solenoid regulator valve, and you can see it regulates it to about 130 psi. So all these solenoids are fed a maximum of 130 psi. The way that works is that line pressure from the pump, as you can see here, is drawn by the arrows. It comes in here and it has a way to get into the solenoid feed circuit. And it starts feeding these different solenoids, the on-off solenoids, the PWM, the linear solenoid, all that good stuff. But it also goes through and allows some of that solenoid to work off this balance end or reaction end, whatever you want to call it. So as solenoid feed pressure raises in that circuit, it's going to be pushing on the back of this solenoid regulator valve. Eventually what's going to happen is that solenoid regulator valve is going to move over to the right, as drawn there, to the point where it blocks off its own supply there. It won't be able to feed it with any more pressure because there's no way through. The passage is blocked off, and that's at 130 psi. Basically this gets blocked off right there. It won't go any higher. They call it a regulator valve, but interestingly enough, after talking with TransGo and their engineer, David, the guy that works with the kind of help designing these kits, he brought up a good point that I never really thought of, that these are more like switches that turn off at 130 psi. Because if you look, if there's ever above 130 psi in this circuit, there's nowhere for it to go. It will shuttle this valve over further to the right, but there's no exhaust to relieve any pressure above 130 psi. And that could be bad because these the pressure that finds its way through these solenoids end up operating on these regulator valves for each one of these clutches, and then the regulator valves control line pressure to the clutches, so it actually might spike some of these pressures higher than expected at these different clutches. So that was kind of a side note there, but assuming everything's working the way it's supposed to, if you look at 130, I'd say 130 psi, but if line pressure is 60, it's going to be 60 because it's going to let everything in there. But once it gets to 130 psi, it blocks off and doesn't let anything higher than that. So anyway, 130 psi, up to 130 psi is allowed to go to all these different solenoids. And then these solenoids are going to deliver, once they're energized, they're going to deliver that pressure to their valves in the valve body that control pressure to the clutches. And this image is kind of nice. It shows, okay, we call it a shift solenoid A. It's used for the 1, 2, 3, 4 clutch assembly. It is normally low. So that tells us a lot right here, basically. When we're looking at, we got shift our A solenoid is going to be controlling the 1, 2, 3, 4 clutch assembly, and it's normally low. So that means when it's electrically off, it's hydraulically off. So it's a proportional solenoid. We've got some that are normally high, some that are low. And here's the shift solenoid D that's going to control either the low reverse clutch or the 2-4 or the 4-5-6 clutch, and that's going to be based on the valve that the shift solenoid E shuttles. Anyway, kind of a lot of information there, but it's all good, right? This chart right here is basically a firing order for those solenoids up at the top. And you could see with our shift solenoid E, that's that multiplex valve that's going to determine what shift solenoid D is going to do. And you could see it's on in first and reverse because they want the shift solenoid D to control low reverse. And then it's off in every other gear because you're going to want shift solenoid D to control the 4-5-6 clutch. Here are the speed sensors. There's really nothing special to show here. That input shaft speed sensor kind of fishes through this hole and reads right off of the input drum assembly, reads right off that reluctor wheel. And through the transmission case, underneath the valve body, we have an output shaft speed sensor, and it's going to actually look right at that gear, that transfer gear. So it could do all of its gear ratio calculations and speed calculations and all that good stuff based off of that. The only thing that's kind of unique about the speed sensors that I haven't really been able to investigate yet is it's described as a 2-wire Hall effect type sensor. So as you may or may not know, most Hall effect sensors are 3-wire sensors. So the thing that this might actually be a magnetoresistive sensor. And I don't know, like I said, I haven't explored that any further. The vehicles that I have are all the GM vehicles, and they put the TECM, the transmission control module, in the valve body or with the valve body in the transmission. So I really can't go in there and check that very easily. Whereas if it was a Ford vehicle, they run those wires out and head to an external TCM. So I could tap into that circuit and find out, but I don't have a Ford vehicle to compare that to. So anyway, long and short, we got 2 speed sensors. One's measuring the input, one's measuring the output. They're Hall type sensors, so they should be creating a digital square wave pattern. But I'm kind of suspecting they might be magnetoresistive because they're 2 wires. Another thing they've got on their electronic schematics, this is the Ford schematic, is they basically show on the floor shifter a switch, the overdrive on-off switch, and that's just basically going to be either a 12 volt or 0 volt signal that you send to the TCMs, so it knows if you're going to be commanding overdrive on or off. It's just it's a momentary switch, so when you make contact, it'll see the 12 volts, and if it sees 12 volts, it knows you push the switch and it knows what you're commanding. This is the schematic for the Ford 6F50. You can see it's pretty simple. All the wiring's coming from the transmission to an externally mounted module. That could be a powertrain control module, it could be a separate TCM. But either way, each circuit is individual, so you can go in and do some diagnostics. That's got to be the nice way to go through and approach one of these vehicles. Whereas like with the GM having everything internal, you're going to limit yourself to the amount of electrical diagnostics that you can do. Really, you can check powers and grounds, communication, that kind of stuff. But with the Ford vehicles, since the module is incorporated in an external module, so it's like a TCM or a PCM, I can actually do some circuit diagnostics, which is kind of nice. Now let's jump into some hydraulics. And this first slide right here is basically showing pressure regulation, how they control pressure in this transmission. And the hydraulics are going to be very similar between the Ford and the GM. I'm just using the Ford as an example right now. We will actually look at some GM schematics. So right down here at the bottom, we have the oil pump. And the oil pump is going to be the source of all of our pressure in the transmission. It is a variable output pump. So right now with this pump rotor, it's going to be rotating in this clockwise direction. It's going to draw fluid in and squeeze it out. And you can see line pressure kind of has its own little passage. And that line pressure finds its way to the pressure regulator valve. Draw that over there. And one of the things it doesn't show here, but the line pressure that comes in is going to turn around and work on the end of this valve right there. And that's going to try pushing this valve over to the left as drawn and compressing the spring. Once that valve moves far enough over to the left, it's going to uncover this passage called a decrease passage. So if I follow this around the decrease circuit, you're going to see it comes back to the pump on the pump slide, on the outside of this pump slide here, and it's going to work between this pivot pin and the seal, and it's going to work on this pump slide to push it over. The more pressure I have in there, the more this pump slide will push over. And when this pump slide pushes over, imagine what's going to happen to the space around this pump. It's going to equalize, and I'm not going to create as much of a suction on the inlet side, and I'm not going to create as much of a compression area on the outlet side. So my pressures are going to drop, or my capacity, the volume of my pump is going to reduce. So that's why they call these things a variable output pump, because it can change its output based off of the position of this pump slide. Right now, as it's drawn, it's in the maximum displacement position. So it's max output because I'm not shuttling. I'm letting the spring right here, which is called a priming spring, I'm letting it shuttle this pump slide into the maximum displacement position. So it's going to be able to create the strongest suction and squeeze out the strongest amount of pressure or volume. And that's going to raise pressure up in this transmission. If I equalize the area around it to the point where this gap would be, the same size all the way around it, I can have pretty much no or either very little or no output. So that's what they do in this transmission. Once pressure builds up to the point where they are satisfied, they got the pressure where they need it, the valve is going to move over to the left, and it's going to let just enough line pressure into the circuit to move this pump slide over to reduce its output. And then once the output is where it needs to be, pressure is not going to climb any higher. And if pressure doesn't climb any higher, we're not going to move this valve over to the point where we're going to uncover this decreased passage, and we're just going to basically maintain pressure. That design is proven, and it's a good system. But the reason why they use it is, I'm sure, way more expensive to build than just a normal gear type pump, is because they can vary the output and they can limit the pump's output to just what it needs, which means you're not unnecessarily moving fluid and pumping volumes of fluid that you don't necessarily need. That's going to reduce drag on the engine and hopefully improve fuel economy. I think that's the whole concept of it all. So that pressure goes to the pressure regulator valve. And this is a very typical setup of a pressure regulator valve. Off of the pressure regulator valve, not only are they controlling overall line pressure, but they're also dishing some of that pressure out to what they call the converter feed. So this is going to fill the torque converter up with fluid. And then another thing that they do is they have a way to adjust that pressure. If we didn't have this LPC passageway right here, pressures would be determined just based off of that spring tension, and it would never climb any higher than whatever that spring designates. But what they do is they go through and they create this variable pressure, this line pressure, and that all comes from my line pressure control solenoid. We looked at the solenoids already. One of the solenoids was electronic pressure control, EPC, or line pressure control. So it's going to take that max 130 psi that comes from the solenoid regulator valve, and it's going to deliver between 0 and 130 psi on this circuit. And then that is going to add to the spring tension. So Not only do we have to deal with the spring at minimum, spring's always going to be the minimum, but then we're going to be able to add to that. And not only does line pressure have to overcome spring, but also will have to overcome whatever the additional LPC pressure is. It's a way to regulate it. The more LPC, the more line pressure we'll have. So that regulates the pressure, and that pressure finds its way into the manual valve. And that manual valve, when I place it in the different gear ranges like reverse or into the drive settings, I'm going to start feeding the circuit with the fluid pressure to do its stuff in drive or reverse. Now let's take a quick peek at what's happening in the torque converter. And this is a picture of the torque converter in its released mode. Here's the image of the torque converter off to the side. It's a kind of a cutaway view. Hopefully you can identify some of these parts. In the middle here we have the stator. I'll just put an S for stator. The transmission side is going to be the impeller. And the engine side, this is the flex plate that bolts up to the engine. We'll have the turbine. So I have the converter clutch right here. This is the piston. It's going to apply the converter clutch right there and engage it to the cover. And when it does that, then my cover is going to drive through the piston. It's going to drive the turbine in the input shaft. So that's typical, right? So I've got the impeller, the stator, and the turbine, and the clutch. The way they deliver this fluid is when it's in the release mode, they're going to go right through the center of the input shaft, and they're going to force the fluid to enter this converter between the cover and the piston. So that's how fluid finds its way into the converter. So there's like no way that the converter can apply when you think the converter clutch. So there's really no way the converter clutch can apply when I'm delivering the fluid between the cover and the piston. And then it finds its way out of the converter, which is kind of backwards it seems like. It actually it goes out of the converter through the apply passage. But they name these passages based off of the torque converter clutch mode, the position that the torque converter clutch is in. And then when it comes out of the converter, you're going to see it finds its way over to the cooler. So that goes to the transmission cooler circuits. It returns back from the cooler as lube and lubricates the gear set. So that is what happens to the torque converter. Hopefully you understand this torque converter and the intro or the basic videos on torque converter clutch operation. If you remember that, I know that's been a couple weeks, but the torque converter is that's a little different to look at from a side view like this, but this is the engine driven component, the impeller, we call that. The transmission, this is splined to the transmission's input shaft, the turbine, and this is splined to the front of the transmission where they have the stator support. So the stator is locked in the counterclockwise direction and it freewheels in the clockwise direction. And the purpose of that stator is that when fluid goes from the impeller to the turbine, it bounces off that stator in the same direction that the impeller is rotating, and it helps with torque multiplication. So that's very important. That was a little bit on what the torque converter itself is doing, and we got to see what this torque converter control valve is doing. And I already mentioned on the previous slide that it's fed with oil from the pressure regulator valve, at least in this release mode. And that's how fluid finds its way in and then into that release circuit. That's kind of the normal state. Torque converter clutch solenoid's off. You can see right here it's a normally low solenoid, so that means when it's off it doesn't have any hydraulic pressure. And that's the reason why all these lines are blacked out. We got pressure coming up here, and it's basically waiting for that solenoid to turn on. And that's going to be the next slide. When the solenoid turns on, you can see now that that solenoid turned on, we got fluid entering in to the circuit. It gets split off and it goes two different ways. One direction it goes to the control valve, and the control valve is going to determine the direction of fluid flow, how it enters the torque converter. So it was going into the torque converter through its release passage before. Now it doesn't do that. Now it goes in through the apply passage. So by shuttling this valve over, the control valve over, we just reversed the fluid flow through the torque converter. And we're allowing fluid from the regulated apply valve, the TCC regulator apply valve. So that same solenoid is not only shuttling that control valve over, but it's going to come up here and it's going to work on the balance end or the reaction end of that TCC regulator valve. Now I've got pressure, basically line pressure coming in from my multiplex valve. I know it sounds fancy and all, but let's just pretend there's pressure coming in there from the valve, and that is going to get diverted right up there to my control valve, and you can see it passes right from there, goes right into the apply circuit. And the way that this applies my converter is that the fluid that's between the cover and the piston, that all gets vented out. You can see if you followed that back, it gets pumped right into the exhaust, right into the sump of the transmission. And then all the pressure going into the converter is fed into this on the turbine side of the piston. So we're filling up this whole volume with whatever apply pressure this regulator valve determines. And since I've got no pressure to speak of on the cover side of the piston, and I've got apply pressure on the turbine side of the piston is going to drift off and find its way to the cover because there's no pressure here and there's a lot of pressure there. Makes contact. Once it makes contact with once the friction material makes contact with the cover, now we've got a seal there basically. The friction material created a seal, and then pressure builds up and the torque converter clutch is applied. The gist of it is that the control valve determines whether we're in the apply or the release mode, and the regulated apply valve determines how much pressure we're going to apply that converter piston with. I'm going to go through and describe how the clutches get regulated. Now this is kind of an interesting setup that they've got going here. They're using the solenoids, PWM solenoids, to control pressure to these regulator valves. And these regulator valves are going to receive line pressure, and the solenoids are going to control the regulator valve and also what's called a boost valve. And the boost valve is basically, and for lack of a better term, it's an engineered leak. So during initial application, when the clutch is just first starting to apply, they're going to leak out this clutch pressure. Then as that clutch starts to apply and the solenoid starts increasing pressure to the clutch circuit, they're going to start closing off that leak, and then boom, we seal that off with maximum pressure or whatever line pressure is. Now we're going to take a look at what's happening here. We've got solenoid feed, which is going to be between like 60 and 130 psi. And that pressure is going to find its way through, and it's going to work on this regulator valve, and it's going to come down to this boost valve. And think about what this boost valve would be like if there was no pressure present. On this end right here, I don't know if you could tell, but these little dots right there, they represent a spring. So I got a spring on this side. And so that's going to be, without any pressure in there, our valve is going to be shuttled all the way over there towards the right as drawn. So the clutch pressure that's coming in here would actually find its way out through this passage right there. And so it's an engineered leak right there. So then as they pulse width modulate the solenoid and they bring fluid pressure in here, not only are we going to be working on the end of this valve, the regulator valve, but we're also going to be moving our boost valve over to the left. And when we move the boost valve over to the left, I've taken off my engineered leak, and now I don't have a place for that pressure to go, and pressure can build up. So in the very beginning of the shift, when I first open this passageway up and I allow fluid to enter into this 1, 2, 3, 4 clutch circuit, fluid is going to be able to find its way over and leak out through that boost valve as it's trying to fill the circuit up. So as they increase the duty cycle of solenoid A, they're going to eventually move that valve over, and it's going to remove that leak, and pressure is going to build up. At the same time, over here on this regulator valve, something similar is going to happen. I've got a spring trying to keep this valve shuttled over to the left, and then I've got this solenoid pressure pushing this valve over to the right. As the solenoid pushes the valve over to the right, I'm letting in more line pressure. So here's the thing. When we look at these newer transmissions, some of these don't have any accumulators in their circuit. So they've taken away the accumulator, the accumulation, through separate pistons and springs, and they're doing it all through electronics. And in this case, they're doing it by regulating the pressure through bleeding pressure off as initially applies, and then trapping that bleed off pressure to let that clutch build as they want it to. So it's kind of a different way of thinking about it. Instead of just slowly bringing in fluid and building it up, they're bringing in more fluid than they need, and they're letting it leak out, and then they're closing off how much leaks out, and then eventually it's completely sealed. So it's not necessarily a bad way to do it, it's just different. So this schematic shows pretty much the same thing, but a little bit different. they've added the circuit that's got this C35R feedback circuit. And you can see we've got this shift solenoid B. This is a normally high solenoid, so when they want pressure to the circuit, they actually keep it turned off. And when they turn it on, they actually prevent the fluid from getting through there. So here they're going to have the solenoid go from an on state to an off state during the shift. So that fluid's going to find its way through. It's going to be going to this section of the regulator valve. That's going to try to shuttle that regulator valve against spring force. And then that will allow this line pressure to enter in and find its way into that 3.5R circuit. Well, that solenoid's also delivering fluid pressure over to this boost valve. And if you remember, in its natural state, when there's no pressure in there at all, we've got this spring that's being shuttled over to the right. All the fluid that would be going to the clutch or could go to the clutch could also find its way into this feedback circuit. That feedback circuit's actually going to help the spring out. It's going to help the spring prevent fluid from getting into the clutch circuit. I just circled the splice, but this whole circuit. And why do I say that? Is because in its normal state, the spring is going to keep this regulator valve shuttled over to the left. And shuttled over to the left, I'm going to be blocking off the passageway that allows line pressure to find its way into the clutch circuit. And then, because in order to get the shift to occur, we have the solenoid energized, and that's going to push on the end of this valve. That's what starts it all when the solenoid hydraulically applies. It moves this valve over to the right, and that lets some of this line pressure into this clutch circuit. And then some of that line pressure that's in that clutch circuit is going to find its way through this boost valve into the feedback circuit, and that's going to help close it back off along with the spring. So it's a kind of a combined effort between the regulator or the solenoid moving the regulator over to allow more pressure in, and the spring and the feedback pressure trying to reduce it. So it's balancing between those two. And eventually, when the solenoid pressure climbs high enough, as they turn the solenoid off, remember this is a normally high solenoid, as they turn the solenoid off and solenoid pressure builds up to a point, this valve moves over to the left far enough and it blocks off that feedback circuit. So basically, we just let full line pressure into this clutch circuit, and we've got our shift, our 3.5R shifted smoothly. When you think about what's happening here, is these solenoids are controlled precisely. They got their PWM figured out. They're adaptive. They're learning how quickly these shifts occur, and they could tweak these solenoids so that they get the pressure rise and the clutch application to be exactly how they want it. And by using this solenoid to control pressure, and then that pressure controlling these two valves to control pressure to the clutch, they're able to do it precise enough to the point where they're getting a repetitive or repeatable shift, and without the use of accumulators. Now, GM does use accumulators on the 456. They also use tiny little accumulators that they call accumulators, but they're really for the solenoids, and you'll see that a little bit later when we look at the GM stuff. In this example, this 2.6 clutch is real simple. Actually, it takes line pressure, comes in here. This is like a typical regulator valve, right? That pressure comes in and it finds its way to the back of that 2.6 regulator valve, and as whatever pressure it lets in will join forces with that spring to basically close it off. So this is not a complicated, this is a normal pressure regulator. They don't use the boost valve or anything like that. So as pressure rises in the solenoid circuit here on the end of that reaction land, it moves the valve over to allow line pressure to enter the circuit. And then once line pressure increases to a point and lets that in and works on the spring end of that valve, it'll eventually close itself off and not let any more in. So I guess they felt they didn't really need to have a boost circuit with the 2.6 clutch. Maybe the shifts are smooth enough the way they are. But yeah, the 2.6 regulator circuit is about as simple as it gets. Now, the low reverse and 4.56 boost valve and regulator assembly, its function is going to be determined by the multiplex shift valve assembly, the manual valve assembly. Basically, it's going to determine whether that this solenoid is going to be controlling either the overdrive clutch or the low reverse clutch. But the function of the solenoid and the valves are pretty much the same. The only thing that's going to change is these multiplex valves, which are controlled by shift solenoid E, are going to be determined whether or not you're operating the low reverse or the 4.56. So let's just look at this one. We'll look at 4.56, and we've got line pressure coming into the regulator valve. and that line pressure is going to come out. This is really no different than some of the other circuits. And the fluid's going to find its way through all these multiplex valves, because remember, this is how it's got to find its way to the proper clutch, and then it finds its way over to the overdrive clutch. But on its way there, it is taking that fluid as it's climbing up. It's going over to this boost valve, and when it's in its normal state, before there's any pressure in there, it's going to allow that boost fluid, or it's going to allow that clutch fluid to find its way over through this feedback circuit to the spring end of that regulator valve. So as they increase the pressure from the solenoid into the circuit, the more line pressure they let into the clutch circuit, and also when the solenoid pressure is increasing, it's moving this boost valve over to the left, and eventually they will block off that feedback circuit, and you'll lose the pressure that's in your feedback circuit. You won't have any more help on the spring closing off line pressure at the regulator valve, and then basically you just allow maximum pressure or line pressure to get into your 456 clutch. Okay, here's a horrible analogy, but I'll try anyway. Let's pretend we're in the shop and I got an air line, right? And I've got a quarter turn valve over on one side and I got air nozzle on the other side. And I got a pressure gauge in between the two. So if I have my air nozzle squeezed, so I'm blasting out all the air, even though there's no air yet, it's turned off. The quarter valve is turned in the off position, but my finger's on the trigger of the air nozzle, so all the air that would be in there is out. Now I start opening up my quarter turn valve, letting air in. But I've got my finger on the trigger of the air nozzle already, so it's bleeding out. It's just bleeding out into the air. How much pressure am I going to be building up in that circuit? Very little, maybe none. It depends on how much flow I can get out of my quarter turn valve versus my air nozzle. But as I start releasing my finger trigger off that air nozzle, and as I start opening up the quarter turn valve more, the pressure is going to start climbing. So they're accomplishing the same thing. The regulator valve is going to be my hand on the quarter turn nozzle. It's going to be determined how much gets in the circuit. And my finger on the air nozzle is going to determine the boost valve, how much gets bled off, and then eventually I don't let any get bled off and I allow pressure to build up completely. So that's my horrible analogy, but that is what they're doing with most all of these clutches in here. At least all of them that use a boost valve and a regulator valve. The boost valve is really a bleed-off valve, if you will, and the regulator valve is what's controlling the pressure, the ultimate pressure that's entering into that circuit. Let's take a look at how Ford does their oil cooler. They do use an air-to-oil cooler, and this is a bypass valve that they've got right there. And there is, until the fluid temperature gets high enough, the fluid coming out will actually just turn around and go right back in. And then once the fluid gets high enough, it gets diverted and it goes through the air to oil cooler. So this is like a radiator. Air flows through it, cools off the oil, and then it comes back. It leaves as red fluid and comes back as blue fluid. I don't really know how that happens, but it's pretty amazing. This image here shows some of the service things that you can do to this transmission. Obviously checking the fluid level and condition, that's pretty self-explanatory. The solenoid body and strategy. That is something that Ford does. They have a software strategy and a solenoid body ID that's got to match. It's got to match what it says in the TCM. Basically, they measure the flow rate from these solenoids, and they can vary enough to the point where they're going to go through and have a table built into the TCM, where when you enter the solenoid calibration numbers, it kind of gives the computer an idea of how these solenoids are flowing and how to adapt for that. So performing a shift point road test, in the service manual, they're going to give you information on when shifts should occur. So that way you can see if they are shifting when commanded, and if they're shifting late, then you're like, okay, usually it's some kind of input, like a temperature input or a load input that's misleading the transmission control module or the PCM to think that needs to delay shifts or something. Inspecting cooler lines, shift linkage check, checking for DTCs, line pressure test using a pressure gauge. There is a pressure test port. You can only check line pressure. Doing a stall test, and we'll look at that here in a minute. Review PID data. Look at some of the scan data that we have available. Inspect the valve body, and of course inspect transaxle. Those simple little things, but the ones that we're going to focus on here are the solenoid calibration. We're going to look at the shift points just as an example. We're going to talk about a line pressure test, and I'll show you there a little slide on their stall test. It's nothing too complicated, but there are test procedures that are identified in the service manual, and there's things that we can do to aid diagnostics. As I mentioned, solenoid calibration is something that Ford does. It's specific with Ford. You don't have to do that with the GM because the transmission control module and the solenoid assembly are all in one. So that was done during the manufacturing of the Tecum, and you don't have to do that. But here on the Ford, the TCM is external to the transmission. So you can have a different transmission, a different solenoid pack. So you got to marry those two together. They have to learn, the TCM has to learn how those solenoids function and control. So they have specific flow rates, at least so they say. And you need to know these calibration numbers, and because that way the TCM could use the proper tables that are kind of programmed into the software to be able to adapt for that transmission to be able to control it properly. So the number on the valve body is going to contain the information needed by the TCM to be able to figure out what the flow rate for these solenoids are. And on the transmission case, there's going to be a sticker somewhere that has the solenoid strategy ID and the solenoid body ID. You can't always look at that and assume that it's all accurate. If somebody's gone in there and changed solenoid body and never entered that information on, you could still see the old solenoid body ID, and you could maybe still see the old solenoid body ID information into the TCM, but yet it doesn't have that solenoid body ID in there. So that's his. So the sticker, if you change any of that stuff, the sticker really needs to be updated with the current information. As far as shift points are concerned, the service manual has information on when the shifts should occur. So you could see in this example here, they say light throttle, the 1-2 should happen between these miles per hour. Or if you're a metric person, you can look at it that way. Heavy throttle, the shifts are going to occur between these speeds. So if you had a customer that complained that this transmission's shifting too soon or it's taking forever to shift, you can go for a test drive, and now you have something to compare it to. Otherwise, you're just taking the customer's word for it. But if it's within spec, if it is, or if maybe you're going to verify the complaint, maybe your 1-2 shifts happening at 20 miles an hour. At that point, you're like, okay, at light throttle, it's driving as if I'm in medium throttle. What are the things that could cause that? So you might go through and take a look at perceived load on the engine, or even temperature, if it thinks it's in an overheat or if it thinks it's overcooled. So you're going to want to look at your PIDs to find out what piece of information is telling it the wrong data to the point where it thinks it needs to delay the shifts. So it's nice having the published specs, because that way you have something to compare what's expected. You got to be happy that at least there is a line pressure tap for checking pressure. Some transmissions nowadays, they don't give you any pressure taps at all. And it's frustrating if you're trying to diagnose a hydraulic problem if you can't even check to see if the line pressure is accurate. So they do give you that, and they give you 2 plugs. One of them's a drain plug, and the other one's a line pressure. Here's some examples of what you would expect with a line pressure test. On a typical transmission, you're going to see at park and neutral, you're going to be between 55 and 60 or 54 and 60 psi. And then when you put it into drive ranges, it's going to jump up to about 85 psi. And now at wide open throttle or stall, so if you have your foot on the brake so the tires aren't going to spin, you're in a safe place. You can see down here they even got the wheels chalked, and you go wide open throttle, you can see the pressures can go 240 to 250 psi. What's causing that? Well, a line pressure control solenoid is going to be delivering fluid to that pressure regulator valve. That pressure regulator valve, that up 130 psi from my line pressure solenoid, is going to be pushing on that pressure regulator valve. And now to overcome the spring and that additional pressure, I'm going to need about 240 to 250 psi, and that'll regulate it to that point. Kind of interesting, they know when you're in park or neutral, so they don't even bother if you go wide open throttle with increasing pressure, because they don't need it. They usually have a boosted pressure for reverse. It will still go to max or more. You can see here at stall, it's 250 to 300 psi, and then when you're in just at idle, you're a little over 100 psi. So they give you some additional pressure when you're in reverse. But these are all tests that you can do in the stall if you suspect that you've got a slipping transmission, you maybe have low pressure, or a harsh shifting transmission, maybe you have high pressure, or a noise, or just transmission that's not quite operating properly. A pressure test is something that you can do, and it provides a valuable piece of information. These next slides are going to cover how GM does things a little differently. As you know, Ford and GM work together on this transmission, but there are still differences. They're not exactly the same. The engineers were probably thinking like, oh, let them do that or let them do that, and we'll do our own thing. So they agreed on most of it, but they tweaked their designs a little bit when they got to production. So the valve body has, in the valves, and some of the hard parts are similar. Ford doesn't use the small solenoid accumulators like GM does. You'll see in the valve body, and GM has these tiny little accumulators. And their clutch pressure regulation is slightly different, but the concept is still the same. As you heard me say a million times already, GM has put their TCM in the transmission on the valve body. They call it a TECM. So it's the Transmission Electro-Hydraulic Control Module, or TECM. That's what they call it. And the solenoids on most of their transmissions of this kind of design are not replaceable. The small little, like the 6040, 6045, they actually have removable solenoids on those. So I wish they kind of did that with all of them, because it kind of sucks to have to, you find one bad solenoid or you suspect one solenoid's bad, is that you have to replace that whole assembly. But yeah, so that is something different between Ford and GM, is where they put their TCM, and the small units have the replaceable solenoids. Even Ford, their solenoids aren't replaceable. It still comes in that whole solenoid body, but at least they don't put the transmission control module on it. They also, Ford never decided to use pressure switches, which you're going to see GM did, and that was something that really, I would say, kind of cursed their early transmission design. And as I mentioned, the larger transmissions like the 6070, the solenoids cannot be removed. It's kind of in this plastic molded case assembly that you would destroy if you tried to get it apart. And even on the ends where they're shown on this illustration, these are all soldered together. So even if you were to try to pull these Torx bolts out and you wanted to get it apart, you'd have to somehow unsolder all these things simultaneously. So I don't know. There's probably some people that are able to get them apart using equipment, but it's not something that you're going to do in your shop. And the first generation 6070s had pressure switches, just like the 6L80 still has pressure switches, but the 6070, the first generation, went up to like 2012, 2013. It used pressure switches to inform the TCM of how quickly these circuits were filling up with fluid, and they've gotten rid of those. And I don't know why, if it was due to the fact that those pressure switch films would break and then they create a bunch of DTCs, or if they just, advance the transmission to the point where they engineered them out. But that is an issue, and we'll talk about that in a little bit. But those pressure switches in the first generation, they like to split, and that's not always a good thing. They'll cause DTCs. They'll definitely cause a transmission to go limp and then come into your shop as with a failure. Just like the Ford, the solenoids are going to control the clutches through valves. We have two on-off type solenoids. And then I've got the solenoids that are going to control the clutches. The 1, 2, 3, 4 clutch, normally low. The 2, 6 clutch, normally low. The 3, 5 R clutch, normally high. Or the 4, 5, 6 or low clutch, which is normally high. And I also have a line pressure control clutch and all that kind of stuff, torque converter clutch that's not all drawn here. But so those are the solenoids that were controlling the clutches. And you could also see when we identify our different clutches, we got the 456, 35R, 26, low reverse. They call this the low and reverse clutch one-way roller or one-way clutch. But it's only used, as you can see, in first gear. So they really should get rid of that reverse part because it's not used in reverse. And I find myself on the overhaul video, just out of habit, not only calling it a low reverse all the time, but also calling it a roller. I can't get that out of my head for some reason. And then we also have this 1, 2, 3, 4 clutch. And all these right here are holding clutches. And then these two right there are input clutches. This slide right here is showing how their solenoids are operating and how they're controlled. And you can see I placed a circle around this one here because that spring is going to hold, in the off position, it's going to hold this check ball off of its seat. And with that check ball off of its seat, it's going to allow fluid into the clutch circuit that they want to control. And if they energize it, they'll actually defeat or work against the spring and allow this check ball to seal off, and any pressure that's in there will get pumped out through the exhaust in the solenoid circuit. So this is a normally high, normally meaning off. So when it's electrically off, hydraulically it's on. And then the inverse is true. When it's electrically on, hydraulically it's off. Whereas down here in the lower corner, it's the opposite. So We got fluid coming in, it's going to seat that check ball and it's going to prevent any of the fluid from going through. And then as they energize the solenoid, it's going to push the check ball off of its seat and it's going to allow fluid to find its way into the clutch circuit. So that's normally low. If you don't have any power, you got low pressure, NL, normally low. It'd be proportional. When it's off, it's hydraulically off and electrically off. So anyway, there's kind of a description on that. I know we've talked about that quite a bit already though. So to kind of go through and look at this hydraulic schematic, very similar to the Ford system. We have actuator feed limit. On Ford, they call it the solenoid regulator fluid. It finds its way into this clutch circuit here. And it comes over to the boost valve. And that boost, it's going to work against the spring on this boost valve and try to move it over to the right. If you think about the spring in its normal position with no pressure in there, is going to keep this valve all the way shut up to the left. And it's going to open up this passageway here between the clutch feed and the clutch feedback. And the clutch feedback is going to be right here. I know it's coming in from both directions. They just don't have everything drawn in the same, on the same screen there. But so in the normal state, when this valve is shuttled all the way over to the left, as fluid pressure builds up into that clutch circuit, it's going to end up working with the spring on the regulator. It's going to come in and push off of this surface area and try to move this valve over to the right. And when it does that, it's going to limit the amount of line pressure that can find its way into the clutch feed circuit. So basically, we just regulated how much fluid we can get into the clutch feed. What we're letting in is helping us close off that valve. And if they want more in, they've got to adjust the PWM on this solenoid to raise the pressure. The more they move that boost valve over, the more they'll block off the passageway that opens up that feedback. The less pressure I'll have in my feedback circuit. And the less clutch feedback pressure here, the more this regulator valve is going to move over to the left, and the more line pressure that's going to get into my clutch feed circuit. Like I said, it's kind of complicated the way they're doing it. Seems like it's unnecessarily complicated, but they're trying to have smooth control over pressure using this solenoid without the use of any other accumulators so that they can control the pressure rise in these clutch circuits. Hydraulics are fun. On this slide, we're just looking at the way pressure regulation occurs. It's the same concept as the Ford system. One thing that they've included is they've got this isolator valve, which is basically just a accumulator for the pressure control solenoid. So we've got actuator feed limit. It has its own tiny little accumulator. And then if you look, the pressure control solenoid has a spring that it works against, so a little piston and a spring. So that's another accumulator. So it's there to smoothen out or dampen out the pulsations that are occurring from the solenoid. And then the pressure control solenoid is going to work on the spring end of the pressure regulator valve. So when the pump starts generating its pressure, if you remember we talked about that, this is right now a maximum displacement. It creates a suction and then it squeezes it out. And when it squeezes it out, that line pressure finds its way, fills all the clutch circuits up. But not only does it go through this to the regulator valve, it pushes on the end of the regulator valve against the spring force until it moves the valve over far enough to the point where we can open up our decrease passage. And once we get fluid in that decrease passage, they can pivot this pump slide over to reduce the output of the pump. And if we need more pressure than minimum is, what did it say, 55, 60 psi. If we need more than that, they let the pressure control solenoid add tension or pressure to that spring. So as we add pressure to the spring side, we're going to need more line pressure to move the valve over to open up the decrease passage. It can't regulate it down and reduce the output of the pump until line pressure finds its way into the decrease passage. Imagine if this pump had very little output and it could only generate 100 psi, but we need 150. Well, there's not going to be any pressure in this decrease passage at all because we would never have moved this valve over to the point to uncover that decrease passage. So the pressure would just be stuck there at 100 and the pump would be putting out what it could. Now we're going to go through with this 6T70 and we're going to cover every single passage on this hydraulic schematic for every single gear. Just joking. We're not going to do any of that stuff. But one of the things that we will look at on this hydraulic schematic is just to get yourself familiar with what we're looking at is we've got all of our solenoids listed out there on the top. And these are like single page schematics that you'd find in the service manual. And this right here, this image, is showing you all your different clutches. We got our 2 driving clutches, and we have our 3 holding clutches. And they're kind of laid out there in the same configuration that they are in the transmission. And you can see we got our torque converter, things like line pressure blow-off valves. We've got our oil pump. And then all of our valves that we pretty much have in the valve body are kind of located there towards the middle. Those tiny little solenoid accumulators. Some transmissions, like the first generation ones, only have 3. Then they added more to them. Ford doesn't ever use them. They don't have them at all. Our actuator feed limit valve is going to take line pressure and it's going to modify that into fluid pressure. All that orange fluid pressure that feeds all the solenoids, that all originates from this one valve. So you can imagine how important the actuator feed limit valve is, because it's responsible for every solenoid receiving their supply pressure, and then every one of those solenoids are controlling their own clutches. So it's a very important solenoid. You want to make sure that circuit has got some integrity to it, and that valve is worked to death. So if we look close at this 2.6 regulator circuit, which on the drawing is way down here. So this is about the simplest pressure regulator circuit that you'll find that can change pressure, because what they're going to do is they're going to balance solenoid pressure on this side. They're going to balance it with spring and their 2.6 pressure. If they want pressure to go higher, they need to add more solenoid pressure, and that will move everything over to the right. And then as it lets more line pressure in, the spring and the additional 2.6 pressure will cut itself off. In third gear, we already talked about how the 3.5R clutch operated on a previous slide, so we'll just kind of take another peek at that, because it is something that they do that's a little bit different than Ford, a little bit more, I don't know, I want to say it's a little bit more involved. When we shift into third, we're basically releasing the 2.6 and applying the 3.5R. So the solenoid pressure is going to be coming in, and it's going to be working towards our boost. I know I'm sounding like a broken record here. And it also works up against our 3.5R regulator valve. And as that pressure allows line pressure to enter in through orifice 34 or past 34, that line pressure also finds its way into the reverse clutch circuit here. When it's in its rested position, the fluid can find its way right into this clutch circuit here. It kind of finds its way into what they call this feedback circuit. And it joins forces, the initial fluid pressure that goes into our 3.5R circuit, it joins forces and works with the spring assembly to move this valve over to the left to block off line pressure so it cannot get in. To get pressures to increase higher, the solenoid is going to adjust its PWM to let more pressure into this 3.5R circuit. That's going to push this valve over to the right, let more pressure in, and that same solenoid pressure, when it finds its way into that boost valve circuit, it's going to move the boost valve over to the left. And when it moves this boost valve over to the left, eventually gets to the point where it blocks off the feed of that line pressure going into this feedback circuit. And if fluid can't find its way into that feedback circuit, and I've lost the fluid in this feedback circuit, now all I have is the spring. So when all I have is the spring, the solenoid pressure is going to be able to force that valve over to the right easier, and it's going to let more line pressure into this clutch circuit. In fourth gear, the only reason why I show this is because we do actually have on the 6T70, unlike the Ford transmission, we actually have a 456 accumulator, kind of just a standard larger spring and a larger piston in there, and it's going to dampen out the clutch for the application of the 456. Common issues that this transmission seems to have, especially on the earlier units until they updated some of these parts, is they broke the wave plate. There's a wave spring in there that breaks, and when it breaks, it spins around and tears up the drum. Normally, people would just buy a new input shaft and drum assembly. Maybe for availability reasons, they'll try to repair it using the Sonnax, and we'll look at this video here in a second. It's like a little a modification. It's not really a modification. It's a workaround, if you will. And these earlier transmissions came with basically too thin of a wave plate that after it's flattened out enough times, ended up breaking and then caused this issue. So GM updated it as an updated wave plate. As a matter of fact, it's recommended that if you took one of these apart and it didn't have a broken wave plate, you definitely want to change it. But in most cases, people are like, change the wave plates anyway, just in case, even if it's an updated one, because they've set up, supposedly they've seen the updated ones break too. Ford doesn't seem to have this issue. They used a thicker wave plate. Maybe that's the reason why. And then Ford doesn't actually have as many wave plates in the whole transmission, all the clutches. And if you take a look at some of the clutches, they don't even have a wave plate. So what can you do to avoid this? You put an updated wave plate in there, or you could do the Sonnax design that not only allows you to use this damaged drum, but it actually makes it so that way their replacement wave plate isn't going to have the same issues. If something were to fail, it wouldn't tear things up like this one does. So let's take a peek at this video real quick.
Hi everyone, Brian here at Sonnax. Today I want to share another innovative solution to a common problem transmission rebuilders face every day. Now this problem has to do with GM 6040 and 6070 transmissions. As you know, they're everywhere out there, millions all around the world, and just about everyone knows about 3.5 reverse drum failure problems in 2007 to 2009 model years. The main problem happens when the weak OE wave plate breaks and gets smashed all up against the drum like this here. It's kind of like silverware in a garbage disposal, leaving you with damaged splines just like this. Now GM tried to fix this problem in 2009 by making changes to both the wave plate and the piston, but we find the updated OE wave plates are still breaking. Whether in stock or rebuilt units, even Gen 2 units are not immune to this problem. So here at Sonnax, we studied the issue to determine the root cause, and we found a simple solution: an improved wave plate combined with a custom steel plate to set correct clutch clearance. It's called a drum saver kit because it not only prevents failure, it lets you restore normal operation even if you've got a damaged drum. And this completely eliminates worries about comebacks due to a broken OE wave plate. Of course, the early style wave plate always gets attention during a rebuild. Even if it hasn't broken yet, like this one, you know you can't risk leaving it in there. But you should also be thinking the same way even for units that already have the updated OE plate installed, because the cost of a failed wave plate and drum during your warranty period is just too high. These drums are not cheap, and neither is pulling the tranny out again, tearing it back down, and installing new parts all on your own dime. Now the waved plate in the Sonnax drum saver kit is shot peened, just like the updated OE version, but we took the design a step further by eliminating virtually all fatigue points. See, that's the corner of the OE teeth right there. And on these broken plates, you can see that every single one broke off at a tooth corner. Even plates that look okay here can have microfractures and be on the verge of failure. But because we removed the teeth from the Sonnax wave plate, we're going to need a way to position it on the drum. And that's where the other part of the kit comes in, this custom cupped steel plate. This is a billet piece. You can see it's not a stamped plate, and these fit together perfectly. This is all you need to prevent failure or to salvage a drum that's been damaged like this one. Normally, this drum would have to be replaced. You can see the splines got all chewed up when the OE wave plate broke. But because there are no teeth on the Sonnax wave plate, there's no hang-up. It can ride near the damaged area without interference. Cupped plate fits right over top. The cupped plate is the same thickness as the bottom steel in the clutch pack, so you can go ahead and throw that one out. This will give you perfect clearance every time without compromising heat dissipation. When I check clearance, it's right on, so I know I've restored normal operation. Now, as you just saw here, this is so much faster and easier, not to mention less expensive, than buying a new drum and transferring the shaft and piston. So if you don't want to risk a comeback, this kit is great insurance, but now you can also quickly repair a failed unit. That makes Sonnax drum saver kits a great way to improve the reliability of all your 6040 and 6070 builds. So go ahead and ask your distributor for either of these kits, and please check out more of our parts for these units at sonnax.com.
Sorry. Okay, so TransGo is a company that makes shift improver kits and performance kits for a bunch of different types of transmissions, including these transmissions that we're covering here. And you can see on this little image I showed you, this is off their website, transgo.com. This is the Gen 1 kit. You can tell that real quick without even reading it because it includes the pressure switches. And this is their generation 2. Less stuff because you don't have the pressure switches. And there's like, you'll see this on the overhaul video, but this retaining valve, or this little spring and retaining clip and so forth, they address that. GM addressed that in the valve body, so they didn't have to include that. But just about all these kits that they have, they're addressing the pressure regulator valve, the AFL valve, the torque converter clutch regulator valve, and also an isolator valve, if it includes it. Now, if you've got a generation 2 6T70 or 6T40, you're going to need to use this reamer to actually go through and ream out part of the valve body bore, so that way you can use these kits and they can seal off properly. They weren't able to make a drop-in valve to address that. You can get just the pressure switch kits. They also have a kit right here that basically addresses those little solenoid dampeners. Sometimes they get worn out, oblonged, and fluid can leak around those little solenoid dampeners and cause DTCs and shift concerns. And with that, you're also going to need a toolkit. That toolkit is a jig that's going to allow you to precisely kind of drill out and machine out those little new accumulator holes for those pulse dampeners, those mini accumulators to fit into. So TransGo creates these solutions for these transmissions that have miles on them. Maybe they got 100,000 or 150,000 miles on them. There's wear throughout the valve body, and it's not necessarily cost effective to go out and try to find a new valve body for something. And so what they've done is they've done the research to figure out what's worn out and ways to address those worn out areas by putting these replacement valves in there. Another thing that they've done is some of the springs and the spring rates and the tensions that they have on there are there to allow for a more precise pressure control. So that way when the pressure control solenoids are operating one of these valves up against a spring, it's the pressure rate and the pressure rise and the pressure curve is going to be more consistent and smooth. We went ahead and used this TransGo kit on this generation 1 6T70, and here you can take a look at the way the valves are set up. Starting out here, this is the actuator feed limit valve. This is the original valve setup, where we've got the valve, spring, and retainer. And this drawing here kind of shows how it's laid out in the valve body. So what they've done is they designed the steel bushing that basically replaces the section right here. And then they made their own valve, steel valve, that fits inside that bushing. And you can see the cross-drilled holes. That's going to still allow the fluid passages to operate like they're supposed to. But what they've done is they've bypassed the wear that exists on this valve body by putting a new sleeve in there and having a valve operating within their own sleeve, which of course that requires their own spring because they've just kind of shrunk things down. And by putting more coils on their spring, they're allowing for a finer control of spring rate. This little spacer right here is designed to allow this spring to kind of stay guided in the center of this bore. Normally they'd have this big old spring inside this bore. Now we've got a much smaller spring, so that spacer kind of keeps that spring guided and along the line. So this is a pretty nice little modification. Talking with TransGo, they said that this is the number one area of concern that they've got in these transmissions, is this actuator feed limit. So they spent a lot of time researching this system and engineering a replacement valve that will last a lot longer and restore function to this accumulator circuit or actuator feed limit circuit. This is also another modification they've done, is they've kind of got rid of the isolator valve. It's the circuit's still there. If you remember what the isolator valve does, it's basically like an accumulator for the pressure control solenoid circuit. So this is the original setup right here. And you can see there's the retainer, there's a plug, a little end plug, and then there's the actual isolator valve and spring. So pressure control solenoid fluid would come in on the hydraulic schematic or on the valve body diagram. Pressure control solenoid fluid would come in this area, and this spring would just dampen that out. Well, what TransGo has done is they've pretty much eliminated the accumulator function of that isolator valve because they feel that it's not really needed. And what they've installed here is on the inside of this little plug, this bushing, there's a little tapered seat. And that check ball that you see there, that check ball seats into this little tapered seat. And the spring keeps that pushed in there. So that fluid circuit basically will work up against that check ball. Now normally that check ball would never open up, but they engineered the spring so that way when the pressure exceeds a predetermined level, I don't really know what that level is, but let's just make up a number. Let's say it's 150 psi. When pressure exceeds 150 psi, it lifts that check ball off of its seat and allows that fluid to exhaust out. So it's basically a pressure relief valve. And what they found is that when these circuits failed, the AFL circuits, pressure regulator circuits, when they failed, they overpressurized the transmission, and that ended up causing part failure, causing part breakage. And they attributed that to an overpressure situation. So instead of having an isolator valve in there, they went ahead and put this basically pressure relief valve in there. Basically, they're not letting the pressures go above a predetermined amount, so that way we don't overpressurize the transmission. This valve right here is the torque converter clutch regulator circuit, and the original valve is this one on the bottom. Now this slug, an end plug, and retaining clip was with the original setup, and they had you move those up, and they basically provided you with a spring and a valve and said reuse these pieces. So here we've got the slug and the end plug and the retaining clip, and then there's our valve and spring. So what they found, you could tell by looking at the difference between these valves, they must have discovered some wear that occurred where this valve rode, because they made this section of the valve longer. So they extended this part of the valve into the circuit longer, so that way any wear that occurred in the valve body, now their valve is going to ride in this this previously unused portion of this valve body. So there might be excessive wear in this area, but now this valve is going to utilize that whole area there. So that should improve that. One of the other things that they did, and it's probably hard to see in this video, is they added a Teflon seal. So there's actually a Teflon seal on that replacement valve. So that Teflon seal is going to seal off against any valve body bore wear that exists in that area there. So it's going to prevent any leakage from occurring between these two circuits there. So they've done a little engineering on this with the Teflon seal and then the elongated valve spool area that they've got. Then of course they changed the spring to kind of match that. The spring fits inside that valve a little bit. This is a pretty nice little modification. This is just kind of a small modification, but it's important nonetheless. On the original torque converter clutch control valve, they have this little retaining plate there and a really small spring, and there's really nothing to kind of keep this stable. So here's the spring, and this little clip went in there. It basically, it's super small and it sat on there. And they found that at times when they take the transmission apart and the valve body apart, that this spring would fold up on it. It would just kind of do a 90-degree turn in there. So they designed this little retaining plate that has a dimple. And so the end of the spring kind of fits inside that dimple and it prevents it from moving around. And that's a nice little modification. That's the only thing that they've done in that torque converter clutch control valve circuit. But imagine if that spring wasn't working the way it would, that torque converter control valve, which determines whether you're in the torque converter clutch apply or release position, if that got all screwed up because the spring wasn't working properly, then you're going to have a bunch of DTCs that are related to torque converter clutch operation. All because of a unstable spring seat. In the later models, if they have you look in this area of the valve body to see if there's an aluminum ledge or step, if you see a kind of aluminum casting in there, the OE's already made a modification to the later valve bodies to add more stability for the spring to prevent it from curling up like that. But if you have an early unit, like a 2008, there's a good chance that you have the early design and you will need to use this little clip and spring to improve upon that design. Here we're going to look at a few slides talking about vacuum testing and the pressure testing. And these are some specs that Sonnax provides on their website. These numbers may vary based off of not only your location, obviously the higher altitude you are, the less likely you're going to get as strong of a vacuum pool, but also if you just kind of take a look at a hydraulic schematic and feel how important some of these circuits are as far as their seal is concerned. Like if you were to do one of these and you actually saw 18 inches of vacuum instead of 20, it still might work perfectly fine. But Anything that's a regulator valve, you're going to want to pay close attention to, because those valves buzz and oscillate. They live their whole life moving back and forth in one little spot. They're constantly balancing spring and fluid pressure against solenoid pressure. And they're sitting there kind of competing with each other and moving back and forth, controlling pressure. So those valves have a higher tendency of wearing out the bores because of their oscillation and them living in one single spot for their whole life. And that's the reason why this vacuum testing can be beneficial. If you go through and you actually check these circuits where the leaks matter, meaning if you got a leak in some of these circuits that you're going to affect the overall clutch operation, if you can go through and vacuum check these to see if they are leaking out excessive amount of pressure, that gives you an indication that the bore is worn or maybe the valve's worn, and you're going to want to go through and address that. You can either address that with like the TransGo kit if they address those areas. Like here, they've got clutch regulators and 3.5R regulators. The TransGo kit does not address these clutch regulators. So that's where Sonnax comes into play, because Sonnax can go through and with a reamer and a new valve or a bushing and a valve, they can restore the operation, factory operation of that. And it's usually better if they're reaming it out and putting a bushing and a valve in there, because the quality of the aluminum of a bushing is going to be way better than the quality of the casting that comes from the factory. So this should last forever. Looking at the AFL, if you went through and checked the AFL valve and check to see what kind of pressures, if you're leaking excessively at the end there, solenoid performance codes, wrong gear starts, clutch failure. Remember, the AFL is so important because it is the feed to all the different solenoids, and the solenoids are ultimately what creates the pressure in all the clutches because it's controlling those clutch regulator valves. The clutch boost valves, for every one of those clutch boost valves, they're the engineered leak, remember? So they've got to operate the way they're intended to, or else we're going to be not venting or sealing off the pressure to these clutches. That's why you can see the shift quality is not load sensitive. Harsh shifts, slips, flares, delayed engagement, burnt clutches, slide shifts, slip codes, a lot of drivability issues here and potential for DTCs. And there's a bunch of different places to check on the valve body because there's a bunch of different boost valves in there. You know, really there's just the 2.6 clutch that doesn't have the boost circuit there. The pressure regulators have got to be good because that's ultimately where our line pressure is generated from. So symptoms that you might have if the pressure regulator is worn out, the bore is worn out, you'd have erratic line pressure, poor shift quality, burnt clutches, converter lube flow, overheating, torque converter clutch, apply and release. You know, remember that feeds the torque converter clutch circuit. So they're going to have you check the regulator in a couple different circuits here. They're going to have you check it. It should be 14 inches there, 18 inches there. And that is an area that the TransGo valve addresses as well with their pressure regulator valve that they put in. It addresses some of the wear that might occur in the valve body. And the torque converter clutch control valve, that's the one that determines whether you're in apply mode or release mode. We're going to go through and check at least this one passage right there to see if it has the ability to switch properly. And some symptoms related to that torque converter control valve are torque converter clutch slip, low cooler flow, overheating, variety of torque converter related issues. And there are a ton of different valves, replacement valves from Sonnax. They do address a lot of the areas within a valve body. When you look at a lot of these, a lot of them require tooling, reamers, fixtures, and so forth. So it can get very expensive. Everything that said zip next to it, it comes in a zip kit. In a zip kit, you can buy this kit. It doesn't require any special tools. They're all drop-in valves. They deal with the way the bores wear in a different manner where you don't have to ream them out. Now, some things you just can't avoid. You have to ream it out. So the zip kits might not fix all of your situations, in which case you have to break down and buy the reamers and buy the fixture. The fixture is something that you can use over and over. It's just a generic fixture, but some of the reamers are required to have these pilots to guide it so that the reamers are going in perfectly straight and reaming out the proper portion of the valve body bore. And so there's this initial investment with these Sonnax. You have to buy the reamers, you have to buy the fixture, and then you could use their valves. So the valves individually, they might be $40, $50, but the reamers could be a couple $100. And the valve body fixture, which you only have to buy once, it's a couple $100. So by the time you add it up, there's an investment involved. But the idea is that the investment pays itself off because you're able to do obviously reuse those reamers and reuse the fixture until the reamers wear out. So you can ream out a lot of valve bodies, put a lot of replacement valves in there. The big benefit of using this system is that when you're reaming out these passageways, these bores, and you're replacing them with the Sonnax valves, not only are you returning it to the OE performance level, but you're also improving upon their design because you're using better quality metals that are going to last a lot longer. All right, that was enough about valve bodies and modifications. You can see there's a lot of improvements that you can do to the valve body side, because when you think about it, the valve body side is what's controlling all these clutches. So if you've got shift complaints, you can have the best clutch clearance in the world, the highest quality frictions and all that, but if it's not being, that the pressures are not being controlled properly, you're not going to get the shift and the durability that you need out of these units. So that's where there's so much emphasis placed on electronic control, computer control, and hydraulic control. And you got to make sure the hydraulics are high quality and everything's working well to ensure that the unit, the gear train and the clutches and all that stuff, that those are going to survive. Some of the other issues that they've run into with these transmissions are they're real sensitive on fluid height. You're supposed to check the fluid between 180 and 200 degrees. You don't want to check the fluid when it's cold, because when the transmission heats up and gets operating temperature, it's going to be overfilled. And believe it or not, when it's overfilled, your transmission is going to overheat, and that's bad. Pump cavitation, all that kind of stuff. So now you don't also want to check the fluid when you're overheated, because that way when it cools off and gets a normal temperature, it's going to be too low. So the fluid level changes pretty dramatically in some of these transmissions. So you want to make sure you check it at operating temperature between 180 and 200 degrees. And then that way, you know, if the fluid level's proper, then that you're going to be good to go for the overhaul. So the big takeaway on this is that make sure your fluid level is being checked at 180 to 200 degrees. If you just got done overhauling this transmission and you're like, well, how do I know I can't get it to 180 to 200 degrees without putting some fluid in it? Well, that's when you use the capacity specs. You can see here, overhaul 12.5 quarts. You want to put 12.5 quarts of fluid. 13.25 quarts when they say the complete transmission fluid capacity, which means you've got the cooler filled up, all the lines are filled up. So you'll expect to put a little bit more than 12.5 quarts if all that stuff is drained out. And if you're pulling the pan, it's a 6.5 quarts is going to come out of that pan. So that gets you in that ballpark. So that way when you start it up, you can run it, get it up to temperature, and then do the final check. So make sure you go through and take that into consideration, because these are super sensitive to the fluid temperature when you're checking fluid level. And that is it as far as this transmission. As far as the lectures go, we covered the power flow, the mechanical operation, covered the electronics, and the hydraulics, probably the hydraulics more than you probably wanted to hear, but had to cover them. And then also some of these issues and how they can correct for them. Now, the next step is to do the diagnostic case studies, do the scenarios, and see if you can apply what you've learned to these real world problems and see if you can solve those issues.